Alright guys, so um, I just want to make a little short explanation for how to go over this task here. Um, so I'm not going to go ahead and do the hypothesis, I'm just going to kind of talk you through it. So for this part, finding the mass of the blue cart. So remember, this was an elastic collision on an incline where we had this red cart and it collides with the blue cart and they bounce apart from each other, and it looks pretty crazy, and that's because this collision is elastic, so they don't stick together, and it's because there's an external force. Really, there's external force from gravity and normal force. The net force is sort of the the combination of those two that's putting net force on the system, just like it would be with a single object on an incline. Um, but it really makes it a lot more complicated. Let's just go ahead and watch it. All right. I'm going to go ahead and open this thing up in Logger Pro, at least as best I can. Oh, don't do that. There we go. Okay, so now we're looking at position versus time graphs for both of the objects. Just to clarify, we can really sort of tell that in the position versus time graph up here, the green actually represents the red cart, which was initially moving to the right. See how it's moving to the right? And the red represents the blue cart, which is moving to the left. And they collide with each other, and both of them change directions. Right, this one starts moving to the right, and this one starts moving to the left. We can also see that neither of them have constant velocities before or after the collision, right? These x versus time graphs don't have constant slope, and that's because there is external force. They're on an incline. So depending on which way it's moving, it's either speeding up or slowing down. So we're getting curved lines here. We can see that just by looking at the velocity versus time graphs too, right? We have these steady sort of downward slopes in our velocity versus time graphs, which would imply that both of our carts are experiencing a negative acceleration, sort of excluding that time when they're actually in contact with each other. So if we want to find the mass of the blue cart, well, what we can do is we can kind of restrict our analysis to just that really short interval where they're actually colliding. Because over that really short time, the external force doesn't really provide a significant impulse on the system. So there is some impulse on it. The external forces do alter the momentum of the system a little bit, but over such a short interval, we can essentially ignore that. So what you could do now is you could look at the total momentum of the system before the collision, which would be m times v of this object plus m times v of this object, which would be negative, and put that equal to the momentum of the system after the collision, which would be the mass times the velocity of this object plus the mass times the velocity of this object. These would have negative velocities. And then what you could do is you could solve for the mass of the cart that you don't know, using the mass of the cart that you do know. So fortunately, though, for us, we can kind of tell just by looking at it that this cart has a change in velocity that's exactly equal to the change in velocity of this cart. Right? You can kind of see how this delta v here, right, is pretty much the same as this delta v here. And that leads us to sort of conclude that both the carts have to have the same mass, because we know that the impulse on both the carts has to be the same. So since we know that the red cart has a mass of 0.505 kilograms, I can come back here and I can actually put in the center of mass. So let's see here, 0.505, is that what it was? Yeah. Okay. And now I've put in a center of mass series. We can actually see it in the video. Oh, my alignment's a little bit weird. Don't know why that's all raised up a little bit. Maybe let's just do our best to kind of ignore it. For some reason we're tracking like above the carts. Well, let's not bother. Let's just go ahead and look at the graph. So let's go ahead and add center of mass x. There we go. We get this nice solid curve. And let's add the center of mass velocity to this one. Cool. Oh wait, no, that's center of mass x. Come on. There we go. Okay, so if we look at the graphs of the center of mass of this system, it's actually pretty regular. Remember, the data is not perfect because I sort of tracked these points by hand, clicking on the video, but the position time graph has a very clear curved slope. And it's actually a parabola because the object is slowing down, the center of mass of the system is slowing down at a constant rate. That's why this has a constantly decreasing slope. If we look at the velocity versus time graph, well, if everything was perfect, this would be a straight line. And we would have just a negative slope of a straight line center of mass velocity graph. We can also sort of tell if we look at the center of mass graph, it stays right in between the two objects for both the velocity and the position graphs. So let's go ahead and look at what we should do with this. Okay, let's look at this part, the total impulse on the two-cart system. So if we wanted to find the total impulse on the two-cart system, that would be the change in momentum of the whole system. Now, there's really two ways to do that. One of them would be basically finding the external force on the system. That's the force on both of the two carts from external forces, and multiplying by the time over which the forces act. The other way to find the impulse on the whole system is just to find the change in momentum of the whole system. So to do that, what I would actually do would be to think of the whole system sort of like a single object, and take the mass of the whole system and multiply by its final velocity to get the final momentum of the system. So you would just do mass of cart 1 plus mass of cart 2 times the velocity of the center of mass, final, and then subtract that from the initial momentum of the system, from which you could just do the mass of the two carts added times the initial velocity of the center of mass. Sort of the bottom line for this is, even though you have this collision going on and it looks like really complicated motion, to understand the momentum of the system, all you really need to do is take the mass of the whole system and look at the velocity of the whole system through looking at the center of mass velocity. Right? And actually it turns out that the center of mass will basically behave as though you just had a single block with the mass of the two carts accelerating up this incline. I hope this was helpful, and please let me know if you have any questions. I know this video is not like super good with lots of, stuff, but I just wanted to give you something because we kind of rushed through this at the end of class.